Okay, guys, so welcome to this presentation. I'm Richard Petrie from Vonac, and also on the call is Paola Genovese from Genetics.
Hi, everybody.
So today we just want to talk to you a bit more about our CXI PT5500 utility pole tester and explain a bit about the technology behind it. Okay, so first of all, I imagine it is the same with you guys as we tend to find around the world. And it's been this way for many years. There are a number of limitations with this technique, as we know. It's and subjective test technique, very much dependent upon the tester involved. It's very much restricted to inspections at ground line, and if we want to inspect the pole below ground, like. To address this, what we have is a device which is unique in the market and makes a quantitative and objective measurement of the pole under test. Essentially, we are trying to help you answer three key questions. Is the pole safe to climb? Is it okay? So why do we need this? Well, first of all, there is the issue of employee safety. We want to ensure, of course, that poles are safe to climb. Additionally, public So, just a bit of information. I often present this slide, and although it is the story is very much the same. That it used to be the case that we had treated with a good preservative like creosote, which in many countries, unfortunately now, is a banned substance. And it was often common poles would last 90 odd years and might not even be inspected until they were 30 years old. And end-of-life disposal was very easy. There were no real issues. However, things are quite different today. Now we're finding that poles that we had 10, 15 years ago, because again, certain chemicals have been removed from this. We're starting to find pole failures very early on in their life, and poles might only last between 8 and 15 years. Toxic waste, and so they cannot be recycled. As a result of all of this, we've got some new issues. On the safety side, we're seeing that there is an increase in accidents. This could start to actually affect their operations. From a cost element, end-of-life disposal costs have gone up, have significantly increased due to the toxic chemical issue, and because the pulls are not lasting as costs. So, some key we want to solve. We want to eliminate the pulls in our network that are unsafe to climb. We want to reduce accidents and to ensure that our workforce can once again gain confidence that the pulls that they are climbing are safe. Additionally, on the cost side, if we can, through doing objective testing of pulls rather than a subjective test, tests. So with our device, we believe that we've got a product that is ideally suited. Can a device be used to hold the line up, and how far away is it from the pole needing to be replaced? And this is because we're providing a quantitative and objective measurement that is non-intrusive, only dig. Now, sometime then, okay, this is all very interesting. What we would like you to carry out a trial, and they were happy for us to share with other customers. And essentially, when I say the trial, I should say, and essentially what they did was they said, we are going to test 200 poles using our technicians and then using your device. Once we have done this, we will remove the poles from the ground and break them in a laboratory. Here is a matrix where we have the lab result reporting whether the pole was good or bad, and whether our device said the pole was good or bad, and whether the technician said the pole was good or bad. And very interestingly, in both cases, there was never any situation where the device said it was good and the lab said it was bad, and also for the technician. So the customer was pleased, in fact, that their technicians were never marking a pole to be good when in fact it was bad, because obviously this would be a significant safety risk. And this is essentially because an element of this was the number in the bottom quadrant, the yellow quadrant here. This was where the lab had been good, but the technician had said the pole was bad. And they got a very high score here, 25% of the poles tested contrasted with our device, where we had a score of only 2%. So the customer and ourselves, we had quite a lot of conversation, 25%, because this seemed extremely high. The guys were being monitored when they were doing this testing. They knew they were in this pilot project, and so they were being more cautious than usual. The customer was expecting that normally they believed would result in a score of between 10 and 15%. Just a little bit of, let me just go up. I should explain. Earlier on, I mentioned 200 poles. Here we see a sample of 199. Essentially, this was because one pole was damaged in the lab. Just a bit of information about how this. So here we just see an image of the guy doing the pole testing itself. Once the pole test had been done, the pole was lifted out of the ground, taken to a lab, and here we can see where the pole was broken. And when we talk about breaking it, what we're talking about is actually breaking the pole to measure its ultimate breaking strength. And this is done according to a European standard, EN 1. Standard. Some additional information to provide you with this is from a different customer who was happy to provide this summary for to use now device. That went down to a replacement rate of 78%, giving them a saving of around 4,800 poles each year, resulting in a saving annual of 1.2 million euros. I apologize for that being euros rather than dollars, but I think currently that's about 1.1 or $1 million per year, something like that. Additionally, of course, there's the cost of disposal. With 20,000 poles being replaced each year, that was still a very costly exercise. So, a summary of what our device to provide non-invasive measurements in a non-destructive quickly and easily. The device is handheld and portable. So once we've performed a test, and I'll explain shortly about how we actually do the test, we get something from the device called a strength assessment. What we can see here is essentially if we apply a load referred to as LC, 50 centimeters from the tip of the pole, the important point is that our strength assessment must be greater than a threshold that we can apply, because obviously we want to know whether it's a good pole or bad, and in a moment I'll talk about the threshold. Essentially, we want to know that our strength assessment is greater than the threshold that we will determine whether a pole is good or bad. So, how do we run the test? First of all, let me just go back. We can just see the probe here in context on this pole. It's just a quite simple device of about 4 by 5 inches in size, something like this, and it's held onto the pole with an elastic strap, and we have a smartphone or tablet that has a user interface that communicates through Bluetooth to actually manage the device. So on the device, we have to enter some very essential information first of all. Things like what's the type of wood? Is it pine, Douglas fir, etc.? The preservative, the size of the pole. It's important that we provide information about the pole size. So what we do for this is, as well as providing its height in meters, we also take some basic measurements that I'll talk about a bit more in a moment. But essentially, this is to do hit onto the pole. And this is just one single sharp hammer hit that is vibrating the pole, and we then do some vibration, as we see here, basically taking into our algorithm the data inputs we've provided in terms of the type of wood, the dimensions of the pole frequencies that are generated from the hammer hit. We feed this into our algorithm, and this allows us to provide the strength assessment in kilonewtons. And here we see a good pole given a score of 3.5 kilonewton, where in this case, for a pole of this size, the safety limit where a pole would break would be at 2.23 kilonewtons, and what we refer to as a standard new pole limit is 3.39 kilonewtons. What do I mean by standard new pole? Quite often, our customers, we want to understand if a pole has reached 65% or use. Some customers changes, say 75% easily. So why does a pole inspector, linesman, want to know about the strength assessment? Let's just go back for a second, because we also see this important point, the factor of safety. Essentially, how close are we to the failure threshold? And in this case, we are 1.7 times the failure threshold, so that's fine. Okay, and additionally, for purposes, we also want to know some information about where is the pole, when was the test done, we also include information about G, etc. So the question about is it okay to use, essentially what we're talking about here is that the pole load, what we're trying to see here is plotting of the pole strength against time and whether it's able to hold the line up, and when it won't be able to hold the line up as time is. And this is essentially considering, is the strength assessment greater than or less than the safety limit being the maximum admitted pole load. So how do we do this condition assessment? So here we see 3 examples where we can see the pole in a good condition at 3.95, a bad condition where we are below the safety limit, and the amber condition, what we often refer to as the pole needs, essentially it is less than 65% of its original strength. Okay, and the other question, what we're just going back a month, so we have this red limit, the safety limit, and then this threshold saved as the pole limit. And it's this that is at 65%. And here we can just see again whether we're comparing the pole strength SA, whether it is less than or greater than the standard new pole limit, so whether it is healthy or whether it needs attention. And so again, this just showing the 3 conditions of the good condition, the need, How far is the pole from being replaced? In the green condition, we were looking at a factor of safety of 1.77 for this particular pole, and meaning that it still has 77% strength of the original strength. In this example, a factor of safety of 0.85, so it's less than the limit, and so the pole should be immediately replaced. And in this amber condition, factor of safety of 0.06, so it's 6% more than the safety limit. So very close. What can we do when we have these results? Well, we can export them into Excel, and this is easily done from the user interface. We just hit the export button, and the results are downloaded into the download directory. So here we see a typical summary view. Here we can see all of the poles that have been tested, whether they're in the yellow condition, green and red, and information about the location of the test, the time and date, factor of safety, etc. Then if, for example, on the red one, I wanted to push into the details to see more information, to see the pole certificate, I could just click on the view button here to go into the detailed view, which looks like so. So here we can now see the strength assessment, and that is compared to the new pole limit and the safety limit, and therefore shown as the actual factor of safety as well. And again, the information about GPS coordinates, time and date. But also down here, now we have noted, here are some observations that the technician has entered about whether they've observed any damage, cracks, etc. One thing to just mention is we also want you to understand where the device can be used and where it's not suitable for use. So essentially, what we can do is to test all poles that are essentially a single structure, whether that means of a road. An area where the device is not suited, just so that we're clear, is, for example, H-frames or H-poles, as they're sometimes called. In other words, two poles connected together, which may be mounting a transformer on them or something like this. And the reason for this is because one pole will impact the vibrational analysis of the other. So because of this relationship between the two, we're not able to test the H-pole. So when I talked about, here we see cables all just running through in the same direction. This is absolutely fine, multiple level. But at this moment in time, if there are cables at different levels going in different directions, at this moment, they are currently out of scope. I do stress at this moment because this is a product that is always so. Essentially, what we're able to provide is a strength meter that can report the maximum bending loading for a given pole. This is ideally suited for asset and pole inspection staff who are wanting to do a cyclic pole measurement campaign. Additionally, also suited for people who want to do a pre-climb check. And this is done through a technique called vibrational analysis. So it's trying to behind the product. One thing that we know is that any material, when subjected to a mechanical pulse, so this is why, as part of the test data input that we request, we need to take a measurement of the pole circumference in two places to understand the taper. We want what we do after feeding these these physical measurements in software. We then do the hammer hit, as we see here, onto the pole, and we do the vibrational analysis, which means that we get a signal that we then convert from the time domain to the frequency domain, doing a Fourier transform, so that we can look at the frequency response that we get from the pole. In this case, it's looking at a very clean frequency response that we're getting. In reality, quite often we have to deal with a lot more noise than this due to things like cables on the pole, transformers, lamps, etc. And so we have to do a lot of cleanup and a lot of analysis to actually identify in the correct way. And so here, just to explain this a bit more, so we place the probe roughly around 2 meters high. 2 meters is not strict, it's essentially you place it where you're comfortable. Hit the pole with the hammer, and then we see this frequency response come out, what we refer to as the natural resonant frequency F2, but also some additional peaks F1 and F3. We feed all of these into our algorithm to give us the strength assessments. Showing this in a slightly different way, what we're essentially doing is inside the device there are two accelerometers, and they are providing us with this signal from the hammer hit that we do the Fourier transform on, and then we do a lot of signal processing in collaboration with some supports from some research we've done in the Padova University in Italy to So when we are entering information about the pole size, we also do some enter some other information into the user interface. That is, the questions regarding how many cables are connected to the top of this pole. Are there any transformers, cross arms, etc.? And we enter this information into the user interface. Just a little bit of background, a bit more information. So if we know the pole MO, and this just a chart here showing the relationship between the modulus of elasticity and the MOR. So what we need to do is to take into our device the pole geometry, other parameters to do with the pole, like as I mentioned a moment ago, the wood density. Also in the user interface, we enter what type of is it in. We need to know essentially, is it hard, soft, or medium ground, etc. And then the other bit that we feed into our algorithm is the pole frequencies that we get the hammer hit. All of this is fed into the patented algorithm to allow us to have the pole strength. Just a bit of information for you. This is an image of part of the laboratory facilities that we have in Italy. This just allows us, in some cases, we might come across a pole world. Okay, Paula, I always like to hand over to you for this slide. Do you just want to talk us through this one?
Yeah, Richard, here I am. This is in this slide, we want to better explain how the safety limit is calculated. The safety limit is the threshold meaning that during the design phase, this is usually a value which is recommended by standard and by utilities. This is the maximum admitted pole load for this pole that I'm measuring. How it is calculated? What is usually done is that the utility decide a design FOS, the factor of safety. So from the standard, from the recommendation, it is known which is the pole average, the pole mean strength. So from the pole mean fiber strength and the geometrical dimensions, it is possible to calculate the pole mean strength when it is new. Then this is divided per this factor of safety, which value is usually 2.53. In this way, it is possible to find the maximum admitted pole load, meaning which is the maximum load that pole will be charged, loaded during with cabling and so on during the installation phase. If we can measure the strength of the pole and grant that this is more
Okay, so this is essentially the end of the presentation material.